So I think I'll get started now, unless anyone has any strong proposals to the contrary. All right, so I'm continuing my lecture series on proof automation in Calc. And recall last time I talked about the style of LTAC scripting, where we basically write programs in a dynamically typed language that manipulate the goal and split goals into smaller ones until there are none left. And we saw a reminder of this style with the way that Andrew approached the prodigious case analysis in the red-black tree proof. And I'm going to use a little bit of that style in setting up individual ingredients in what I present today, but my main focus is going to be an alternative approach to proof automation in Calc, also applicable to other proof assistants based on type theory, and that approach is called proof by reflection, and it has pros and cons versus the more ad hoc scripting approach. And I'll do a few examples, all inspired by definitions that you've already seen in earlier stages of this summer school. And I'm going to start out by looking at, actually just a second, I need to tweak something here. Now I can't remember how to, hold on, change my Calc version between. While that's running, I'll continue the explanation. So I'm going to be working with the same imp language that we've seen a number of times, and I'm going to be focusing on something very basic at this point, reasoning about what we know about the result of running a concrete imp program, and building some automation to help us do this seemingly straightforward kind of reasoning. And this is going to add sort of one of the two key ingredients of proof by reflection. And then afterward, I'll look at another example of a category of proof that's come up in other lectures and add the rest of the ingredients that together make an approach truly proof by reflection. And we'll see how this works and what are some of the reasons we might prefer it over the ad hoc LTAC style. So let's see if this is ready to go. OK, so one thing I'm going to do, the amount of sophistication in this block of code here is maybe overkill given what I'm going to use it for, but I just want to be able to write imp programs that look more like we're used to. And so I use notations and coercions to set it up so I can just write a string for a variable name instead of anything else wrapped around it. And other meta-level remark, you will not find any of this code in the DSSS17 repo. I'm pushing it after class. This is at least the way my mental model of these lectures works. Most of us are going to be surprised by every line of code that pops onto the screen. And this is a feature, not a bug. And I'll push it afterward. So here's a function that's going to generate a nice infinite family of imp programs. And this is the keep adding family, where we're going to just keep adding 1 over and over again to the variable x. And then at the end, we'll skip. So for instance, if I run this with the argument 3, then we get x equals x plus 1 3 times, ending in a skip. And we can bump that argument up as far as we want. This is going to give us a way to sort of performance test the automation that we build for symbolic execution of programs. And I'm also adding a bunch of facts from the Software Foundations library that will be helpful in doing proofs. These are all facts about the behavior of update operations on these finite maps that, yes? Using congruence says when one of these facts, one of these theorems has a premise, make sure congruence proves it or don't apply the theorem. Congruence is a complete procedure for equality. Yes? Let me mentally enclose these in the tags for hoping not to explain in detail, but feel free to ask anyway.
What are coercions?
Coercions are functions you can register that when you have a coercion from foo to bar and you write some term in a context that needs a bar, but it's actually a foo, Calc looks in the coercion database and says, oh, I know how to bridge that gap. I'll run this function for you to turn your whichever one I said into the other one. Yes?
The thing about using congruence.
Uh-huh.
Is it
This one.
when you decide to rewrite congruence, or is it with a not rewrite?
hints are used by a tactic called auto rewrite that I think I didn't get to talking about last time, but it's a tactic that tries to repeatedly use all the equalities that these facts prove to replace the left-hand sides with the right-hand sides until there are no more matching subterms. Yes?
Can you use hint rewrite using only with tactics that solve the goal, or can you use it with arbitrary tactics after using?
I think you can use it with arbitrary tactics, but the rewrite will go ahead as long as the tactic doesn't fail, even if it makes no progress, which might not be the semantics you want. All right, so let's try to prove that when we take the keep adding 3 program, start it in any state, run it to some other state, then in the final state, the value of variable x is 3 greater than the value in the starting state. This seems pretty straightforward. So keep adding 3 is just x equals x plus 1 3 times in a row. So I'm sure you've spent a lot of time reasoning about the big step semantics of int programs by this point. How would you recommend we go about proving this fact? Any ideas? Intros, that's a good start. All right, self-esteem boost achieved. Let's see if we can go further. Andrew.
Generalize the 3 to n?
Generalize the 3 to n. Ah, yeah, that's what we can do if we're feeling like we're not breaking enough of a sweat. We'll see if we get that feeling later. Yes?
So I think you should be calling a string a plus would be a place, so it should be just called a constructor.
Let's see. Well, first, let me reveal the syntax in detail so we can see exactly what we're dealing with. We have 3 pluses in a row ending in a skip. And you said constructor. But the goal is an equality, so constructor for equality would be when reflexivity applies. And that's not quite what fits here. Yeah? That sounds like a good idea. And I defined this tactic invert that I used last time. So I'll use that instead. I think it's probably almost identical to the iv that we've seen in other lectures. So what this did is it said, all right, you ran a sequence. Well, that means you ran the first thing, and then you picked up from the state that one ends in and ran the second part of the sequence. And at this point, instead of asking, what step should I run next, let me ask, what's the recipe we should use here to prove this goal and probably many very similar ones? Yes?
Repeatedly invert every evaluation thing the hypothesis versus constructor on the left.
Right, and I think we can even remove the constructor on the left part here because I only want to use this on concrete programs, so there will always be a constructor on the left.
Can you repeat what he said?
He suggests repeatedly perform inversion on any hypothesis that is an evaluation fact. And he included the proviso that it should work on a program with a known constructor at the front of it. And I only want to consider cases where that will always be true, so I'm not going to explicitly put that in my tactics. So what I'll say is repeat match goal with, as long as we find anything that's a C eval, takes 3 arguments, don't care what the conclusion is, I'll just invert that. And let's see what happens. Need some more space for this conclusion. So here's the formula we got. Think fast, is this true? It probably is, since the original theorem statement looked pretty plausible, but this is kind of gross looking. What should I do to make this be obviously true? Yeah, we set up these hints that know about the behavior of t-update. So I can say it auto rewrite with core. That's the hint database our hints go to live in by default when we don't specify a database name. So when I run that, things got a lot nicer. And we're almost there. What else do I need to do? Something on the short list of tactics you run when you're just feeling really optimistic that things might get really small without you knowing why. Simple, yeah. And then apparently I should run this again. All right, so this looks really close to obvious. We need to turn 3 plus 1s into a plus 3, and Omega knows how to do that, that's for sure. All right, so let's try to systematize this with a tactic definition that might even work for other cases, like the exotic keep adding 9 that awaits us below. So I'll say what am I calling this? I'm calling this SymExec.
Could you control X1 so we can see everything briefly?
Yeah. This might not be the ideal time for that.
It'll pop up the goals in response afterwards.
This is all going to fit on the screen with a very small change anyway, because I'm just going to use more same line stuff.
Why don't we put this rewrite in the repeat hash goal?
We could. Let's come back to that in a moment. And I'll keep Omega separate. So we have symbolic execution, as a separate ingredient, and then we can do proofs using the result of symbolic execution. So I think I don't actually need this one. Okay, so there's the whole tactic. And what we can now do is say SymExec here, and then it reduces us to this nice point, and then we can call Omega to finish it. Okay, and if we did this right, we should be able to get the same level of automation for keep adding 9, whose name probably gives away what it is. Let's do a little copying and pasting here. That's taking a while, but it gets us to the right point, and I can run Omega, and we're good there. So there was a suggestion I just heard about a change we should make, which might have some impact on this running time. Could someone repeat that and give the theory for why this will speed things up? It was, who was it who said that? Aha, yeah. So what change should we make, and why do you think it's worth making?
I'd say because the proof terms become simpler with the auto rewrite. I would put it into hash goal.
Proof terms become simpler with the auto rewrite. That's probably true.
It gets simpler because you have less parts.
We're shrinking. Some of the intermediate goal states will be smaller because we're doing simplification as we go, and we don't have to keep dealing with huge terms all the way up until the very end. I think that is true. So let's put that inside. I'll just copy this. Something like that. What did I use here in my version? I say, I'll put this on a separate line. I'll make both of these be in star to apply the simplification rules wherever we can find matches, anywhere in the goal. Now, this one was pretty fast before. How about this one? Did it get better? It was a little better. It took like 1 or 2 seconds, which is an improvement over the last time.
I think you can remove the last bit now.
The last bit.
You repeat the auto rewrite the score.
Quite possibly. Let's see what happens when I comment that out. This one's still good. All right, even better. But let's get some more visibility into what's happening inside. I'm going to break out a name for the single iteration of this loop, and we'll just sort of step it through and watch what happens. So SymExec 1 is just running this. And then I'll say repeat SymExec 1. And I'll do it on the big one here. So the intros, and then we can do SymExec 1. I probably want more space for this one. SymExec 1. I'll just paste a few of these in here. We can pick an arbitrary point in this process. Ooh, so now at this point it's broken down to all the atomic statements within that more or less. And watch what's happening at the bottom. All these plus ones are piling up. Can we think of anything we might want to do to clean this up a bit? Yeah. Associativity. Yeah. What kind of tactic code would we use for that? I see. Okay, so for instance, if I use a helpful command called search rewrite, and I say, look for a rule that applies when I'm adding two things together and then adding something to that, then I'm told plus a soak reverse. So captures that one. So for instance, in this case, I could rewrite with plus a soak reverse. And now two of these ones are right next to each other. So if I simple, they'll turn into a 2. So that's progress. So how should I incorporate this into the tactic code? There's actually a way to do it without changing any of the LTAC definitions. We can make this a hint. Let's try that. Let's see how these SymExec ones are different. Hint, rewrite plus a soak reverse. Oops. Boop, boop, boop. Boop, 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 boop. Almost. We'd need a simple in another place for it to completely avoid these extraneous terms. Question? Yeah.
Would it be nice if we were to first do the +1 and then look at the valence later sequences by doing a reverse match rather than match?
A reverse match?
That we simulate actually the first command first before we look at the sequencing later in the sequence.
Yeah. So this tactic relies on Coq to choose the order for which of the hypotheses we're going to invert next, and it seems to be making the suboptimal choice.
Because from top to bottom, we might do the +1 first and then look at the sequence.
That sounds like a pretty good idea, though this version seems like it's asymptotically optimal. We'll always have a little 1+ in there that we might combine with this other number, but we never get arbitrary sequences of 1+s like we had before. But I think it could make sense to tweak this tactic to have some heuristic about the order to explore hypotheses in. And generally, you can have arbitrary trees of sequencing. So you'd have to do something like measure the size of a term to decide which one to go into next if you wanted something completely.
For the symbolic notation, you just want to do it in the same order as you would run the program. So you also
Oh, yes.
do the first case first.
Yeah, we could do that.
Just reverse match and see what happens.
Okay. Where did I put the match? I don't think I've used this command before. Is this how it's written?
Match reverse goal.
Match reverse goal.
I will use the new one.
Okay. We'll have this adventure together. Let's see what happens. Dun, 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 dun. Come on. Something bad happening. Now I don't know what's going on at all. That was magic. Okay. Now we had the addition up here in hypothesis instead of down below. I was looking in the wrong place, and it definitely is not showing us any extra. Was there one there?
In this program, always
Oh.
two
Now there's one here.
only.
Now there's one here.
I mean, you only have two command hypotheses. Because you first split it, and then you do the first one, you get a new
Yeah.
state.
Doesn't we get the same effect by clearing the old hypothesis before using this?
I think that already happens. The invert tactic clears. It's just like the inv that we saw earlier today. Well, this is about the target level of sophistication I was going for in this version of the tactic. But are there any last suggestions before I show another approach? Yeah.
I'm not sure if you welcome suggestions from me. But what about the fact that the T update is actually computational already?
Sort of, except the original state st is a variable, so we can't compute everything about it. And that's part of the challenge here. So we could, in general, write an interpreter for this language. I think there are, for while-free programs, such an interpreter appears in Software Foundations. And that's great when you start with a completely known set of variable values. When you have a variable st, in this case, you might have to do a little bit of work to properly summarize the effect of the program when you can't just compute a number as the answer for every variable, which is the case here. The effect of this program is to add 9 to x. It's not to set x to a particular constant value. An interpreter would give us that second one, but it's not an immediate match with cases where some parts of the program input are symbolic, like x effectively is here. All right, let me put this proof back into nice short form, and we can proceed. So SymExec does all that work, and then we can, now we don't even need omega, we can say reflexivity. All right. Okay, so I wonder what this proof looks like. I think this one's even too big to do that on. I know in the Coq intensive, there was some at least brief mention of what, when you finish a proof in type QED, what is the thing Coq has built internally? Let me just show you that. Here, I think this fits on the screen at some level. There's a lot of stuff happening here. Dun, 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 dun. This is the 3 version. I think by the end I'm going to get up to 100 working fast enough. Imagine how that's going to look. It is superlinear explosion in the size of this internal representation of the proof. And that is a very bad thing for performance. So there are fundamental tricks that will help us get around superlinear increases in term size. And that's what I'll do next. Was there a question?
You anticipated my question.
Okay. So we are in an advantageous situation. The program we want to analyze is already in an inductive type of syntax. So it's already kind of formatted for us to poke at it in a nice way. Does anyone have any thoughts on how we could take advantage of that fact to build some nicer automation here? All right. So far we've been writing LTAC programs, while a lot of other code we've written is in the Galena language. Galena is the language with the very expressive static type system, and it enforces termination of all programs, whereas LTAC is the dynamically typed language that generates proofs that are checked for you eventually, but it needs to generate proofs to justify every step it takes, whereas with Galena, it's like when you prove CompStat is correct, you don't have to rerun the proof for every C program you compile. Can we do something similar to handle this symbolic execution task? Like for CompStat, we already have the syntax of the programs that we're doing something with. We kind of want to do symbolic execution instead of regular compilation.
Well, you could probably prove that doing that thing n times gave the result added 1 to another.
Yeah, I think this was Andrew's suggestion near the beginning. Prove a theorem specialized to the keep adding function that shows that for any n, we get the answer we expect. What I'm more interested in here is consider that we have a concrete imp program, and we want to do fast symbolic execution of it to compute a calc term that tells us what effect it had on the state. What if we wrote a Galena function that computed that? Yeah. Yeah, but it's not quite a regular interpreter because it needs to be a little symbolic, because we want it to work in cases like this where we don't know the starting values of the variables, but essentially we know everything else. We want to be ready for any starting variable values. So there are ways we can do this. Do I see a suggestion over there? Oh.
What if you wrote an interpreter with uninterpreted symbols?
That sounds like a good idea. So in other words, instead of making the variable values be numbers, let's make them be expressions. And these expressions might have variables in them. An occurrence of a variable will mean the initial value of the variable in the starting state when we begin execution. So in other words, for examples like this one, every occurrence of a variable in an internal state of execution will be the value of that variable in this state, st, the starting state of our run of the program. So we're essentially going to build a specialized inversion function in Galena that knows how to give it a fact like this, figure out the structure of st prime in terms of the values of variables in st. Yes?
So you're going to have keep adding produce a description of what it's going to do to st.
We're going to write a function that, given any program, not just keep adding, any imp program, knows how to make that transformation. We're going to write a semantics, but it's going to be a funny kind of semantics. It's not just an interpreter. It's a symbolic evaluator, and we'll see. I'll point out the places where it's different. A lot of it will be the same. All right, so I'll write some of this code and probably copy and paste anything that's left at the point where things start dragging. So let me first define what I'm going to use instead of these variable maps that we've had so far in imp. I'm going to define a symbolic state is a list. This is what you might call an association list. It's a list of pairs of variables and their values. It's going to map each variable that appears in a pair to a particular expression. And now it's not a number, it's an expression. And again, variables within the expression refer to the initial values of those variables when the program starts running. Though I'm not formalizing that in writing this so far. So then we can write a function that looks up in one of these maps, given a sim state, which I'll write sim t for some reason, and given a variable, we can look up the expression associated with it, and this is pretty boring. Let's look in the state. If it's empty, then I'm going to return some default that actually won't matter. We'll sort of prove we never get to this case. Question?
The maps library, though, give you maps from identifiers to any type? Why not just have a map?
Why did I do it this way? Because it's a list, more things are computable, and I forget if I used that somewhere. I think I want this to be efficient, and if I just used what the SF library uses, where you're using calc functions, then when you make multiple updates to the same variable, they're all piling up as a bunch of lambdas on top of each other, and it completely negates the performance benefits of this. So we're not going to allow duplicates in this list. That's the key thing. So if we have some other variable, or some variable, we don't know if it's other yet, ya in there, if they're equal, then I'll give you a, otherwise sim get on the rest. So that's one way to look up in this list, not surprising at all. And let's see. Let's write a symbolic evaluator for arithmetic expressions. It's going to look a lot like an interpreter, which you've seen before, but there will be an important difference. So given an arithmetic expression, we're going to return another expression. And some of these cases will be like normal. For one thing, unlike a regular interpreter, the meaning of a numeric expression is itself. It's still syntax. We don't switch to returning the number. And why are we working with expressions as the outputs of this? Because when we get to an identifier, I'm going to look up in my symbolic state that variable, and the result of this lookup is another expression. But the variables in that expression, again, refer to the initial values of variables, not to the current values of variables. We're going to reduce, as we run the program step by step, we're going to reduce everything to a straightforward function of the original values of the variables. And then these other cases are just going to be, as they say, homomorphic, where we just push operators down through things. And I'll use some advanced Emacs tricks here in a second to save time. Sim a eval. Here comes an advanced Emacs trick. Did you see that? Okay, so this might be right, and I wrote B in where I meant A for some reason. And it's called mult, sorry. Okay, so this is almost an identity function, except everywhere there's a variable, we're going to replace it with whatever this symbolic state tells us it should be. So variables might expand into big old terms on their own. And, but now, we take an expression over current variable values and turn it into one over starting variable values. I think at this point I'm going to copy some of the code for this and just step through it. So we've got up to sim a eval. So I'll just take all the rest of this. So I also have a function to remove a variable from the symbolic state. This will come in handy in a place we'll see. There's another crucial step that corresponds to how we use rewrite hints to turn all the plus ones into just plus some constant. I'm writing a function here that takes in an expression and returns another one that's supposed to be simpler. You can pick your favorite algebraic identities and use them here. And then you have to prove that they're correct, and then everything else will work the same. And the one we need for our particular example is when you have a plus, simplify both sides. And if the left-hand side was a plus of a number, the right-hand side was a number, you can combine those numbers together into one. That's the only thing this function does. And then simset is an operation that corresponds to overwriting what we know of the value of a variable by first deleting it from the list if it's already there, and then adding it to the front. So we just saw this one. Similar function for Boolean expressions. And I have a recursive function that turns a symbolic state back into a concrete state by repeatedly t-updating using the result of evaluating all the expressions we put in there. I won't dwell on the details here, but you'll be able to take a look at this code when it's posted after class. And let's see. This is the central function. This is, let's say, the symbolic evaluator for commands. Yeah.
Can you just go back up 3 lines?
All right.
This is the place where you need to know the domain of the map.
Right. To even implement this, you need to know the domain of the map, and orthogonally, there are performance benefits within the execution process before we get here. So this is a function that has a few twists to it. It takes in symbolic state and a command, but it also takes in a Boolean expression that is essentially recording what needed to be true for us to get to this point in the program. And then the result of symbolic execution is actually a list of possible final states, because there could be different control flow paths that are possible. We need to remember all of them. For each one, we remember a Boolean condition that tells us what needs to be true to take that path, as well as the final description of the variable values in terms of the original variables in the program. Likewise, bexp is only in terms of the original variable values in the program. So for instance, a skip command gives us just one possible outcome. Namely, the state stayed the same, and the condition that governs whether we get here stays the same too. An assignment keeps the condition the same and then just overwrites the value of the variable. A sequence is a little complicated. It uses some folding to first compute all the possibilities for the first command, and then loop over those, compute all the possibilities for continuing from each of those, and then append them all together. And an if appends together the results of descending into both the then and the else cases. In the then case, we extend the path condition saying, by the way, the test was true. And in the else case, we extend the path condition saying, it's also true that the test was false with a b naught. And then I'm leaving out while because it doesn't fit this straightforward symbolic execution strategy. Yeah?
We went really fast over those path conditions. Can you explain again what's the purpose of the semantic intuitive understanding of those path conditions?
Okay, so I'm not handling while loops here. So programs are essentially just, the only control flow comes from ifs. There could be many different paths through the code based on whether a different if is taken or not. And these path values basically record which ifs were taken in terms of the tests that they ran and whether they were true or false. So we could just return all the possible variable values at the end of the program, but some of them will be unreachable given a particular starting state of execution, and the path conditions will help us figure out which ones are unreachable without having to go back and examine the semantics of the program again. I think at this point I'll just skip down to what the correctness theorem is for this overall function, and it is not that, not that, not that. Somewhere around, it was like C eval. Sims eval OK says that if you had an actual execution of a program, and by the way, using this function no whiles from Software Foundations, we check that it's a loop-free program, then run the symbolic evaluator. Here it is at this point. Start it in the actual state. And nil here is the symbolic state. We don't know we have not overridden the values of any of the variables yet. They're all equal to their initial values. And the path condition is true, meaning we don't learn anything from the fact that we got to the beginning of the program. We know we're going to start there. Evaluate this command, and then so this generates a list of possibilities, and then capital E exists as a predicate that takes another predicate as an argument and then asserts that for at least one element of this list, the predicate argument holds of it. In particular, this value here will be a pair of a Boolean path condition and a symbolic state. And we say the path condition is true, and the actual concrete state here is equal to the result of converting the symbolic state back into a concrete state. So this is just a long-winded way of saying, hey, one of these answers actually applies to the true ST prime. The condition we computed for when this answer applies holds, and the answer equals the one that we actually got after the appropriate conversion. And most of the action for that was in a lemma. And I'll just show the end product of this. So I redefine SymExec, where we look at the goal and then just apply that fact in the goal. Maybe I'll run through some of these steps manually in a concrete example. Intros, apply, the name of that theorem is sim c-val OK in H. And then it changes to look like this. So there exists something satisfying this predicate in the list that this expression computes. Let's simplify in H to see exactly what the result of that symbolic evaluation is. There's only one possible outcome. Its path condition is true because there are no ifs in that program. And then the state is the result of replacing x with x plus 1. And that is overridden by replacing x with x plus 2, which in turn is overridden with replacing x with x plus 3. And for some reason, those did not simplify away, but I can unfold simset in H, and then they should go away. So we just get x is replaced with x plus 3. So the key thing is this description here was computed just by running a Gaussian program. We just asked Calc to normalize a functional program. And normalizing a functional program is a free step in Calc's proof system. This does not need to be recorded in a proof term, and I'll be able to show you the much shorter proof term that's generated from this particular proof script. So now that we've seen that, we get sim-c-eval-OK to do essentially all the work, and we can formalize that in this tactic that just finds a c-eval hypothesis, applies this correctness theorem in it, and then matches on the type of that we get after we have done that apply, and does some work to pull apart this exists and consider every one of the cases that corresponds to one element of the list, and then everything is pretty straightforward after that. I think I'll leave that for investigation after class, but SymExec can just prove this goal, and this one, and 12, and 100. Pretty quickly. And what does this proof term look like? It looks like this, and this proof term does grow a bit based on the length of the list that the evaluator returns. This is kind of, I'm surprised this is as long as it is, but I think this proof term essentially will not grow as we increase the number. Let me verify that by printing the one with 12 instead. This feels like the same length, doesn't it? 178 lines, and this one is how many lines? Oops, forgot to finish the proof. 1,000 is pretty long. This is probably still not a good idea. I'll print 100. Whoops. 181 lines. So we added 3 lines going from 12 to 100. Whereas in the old approach, it would be some big quadratic or worse blow up. All right.
What is the brackets? I mean, putting a tactic within brackets that you use it in the second definition of SymExec?
All right, let's take a look.
There,
Reflexivity. This is actually a notation for a list of tactics. They're separated by pipes. And this is saying apply reflexivity to the second subgoal that results from the previous tactic. Okay, yeah.
Relatedly, I noticed that in Andrew Appel's lectures, the metrical with the cases didn't have square brackets around them. What do the square brackets do?
Maybe they don't do anything. I just got used to writing them. Maybe they stopped being required at some point, and I didn't notice.
Okay.
Yeah.
So what will this tactic do if you try and call it when your command starts with a while?
What will it do? It will fail because there's a no whiles hypothesis, which you won't be able to prove. You'll fail to prove false equals true, which is probably a good sign. Any other questions? Yeah. Why is QED fast? Decades of engineering.
Does the proof term annotate that if you switch to the VM to check the question mark?
All right. One thing I didn't talk through is that so we have this application of the symbolic executor to our concrete program. We want to run that to get the answer. And I do that with a reduction strategy called VM compute, which compiles to bytecode to do the simplification, which makes it fast. In fact, I think, yes, the final proof term contains a little hint. You should use the bytecode evaluator here, and that's why QED is still fast.
Does it get noticeably slower if we use eval compute instead, for example?
Good question. And I don't even have to decide what your standard of noticeably is, because I will now give you the opportunity to check. Do you notice this? I don't know. I didn't. This, I didn't notice that. 100. Well, I forget how fast it was before. This isn't great scientific method.
Use time to get actual.
Yeah, we can use time. There's a command called time that we can run to see how long did it actually take. 0.211 seconds, and VM compute would take. That's a little faster. I think I'm not sure if I expected 1,000 to work. I guess
Is the reason that the difference isn't large the fact that you have to invoke the bytecode interpreter, et cetera?
Maybe it's just not a very expensive program, and that's why the difference isn't large. But you're right. There probably is some additive constant factor to start up the bytecode interpreter. I don't know the details. Oh, that one finished. That's good. It took like 10 seconds or so. It would have been, I think this might be in the takes longer than lifetime of universe category for the original strategy. And if not, add a few more thousands and it probably would be. Yeah.
So this method doesn't seem nearly as robust to changes in your proof script or in your definitions.
Which definition?
So like say we change the source language.
Oh.
It wouldn't. I don't think any of your things where all of your pattern matches would have gone through anymore.
You'd have to change the symbolic evaluator's definition and modify its proofs, but then in concrete goals like this one, everything would just keep working unless you change the semantics of commands you're already relying on in individual theorems.
Sure. Yeah. Just like with tactics, it seems like you're kind of trading flexibility because the tactics might very well still get the right answer.
Yeah. You're right that ad hoc symbolic manipulation of goals gives you some opportunities for extensibility that you don't have here without more work. And yeah, I don't think it's feasible for me to go into that more work part, but there are ways we can make this more extensible. Yeah.
So I feel like you're cheating a little bit because the programs that you have don't have any if statements and also don't have whiles, which is what slows down symbolic execution typically, right? Because you're going to get a blow up according to them.
Yeah, it would keep working at least. So if we have fix point, make choices, it returns a command, and we say 0 skip. And prime is, what was it? If b x is less than n something, then make choices n prime else. This is a kind of a silly one that does the same thing no matter what. In fact, it always has no effect. And it was, if I remember the syntax right. Oh, I need to overload. What did I do up here? I can say infix less than equals. What's the name of the constructor for less than in imp? BLT? Maybe. Do we only have less than or equal to? Okay. Let's do this. And then, for instance, compute, make choices 3. That's getting pretty big. And then let's try one of these. I'm not going to do 1,000 because now we're getting exponential blow up in the number of possibilities, though we could be smart and avoid that in some cases. Let's do make choices 3. Make choices 3. And then, well, this should have no effect. That was also an easy one with degenerate ifs, but logic, it's an accurate executor at least. And all those possibilities, is this right? All the branches could happen with different starting conditions. Some of them might be impossible, but there are multiple possibilities that actually could happen given the theorem. All right, I think I'm ready to declare that 3-minute break and switch to the second half of this, unless there are any other questions on this content first. Yeah?
Is there any way to add something like while into this technique?
The classic way is loop invariance, which makes things significantly more interesting. And I think you'll have to deal with that in the crash safety assignments in a sort of similar way somehow, but I think that's based on LTAC, not Galena programs to do the symbolic execution. Yeah?
Couldn't you also just add fuel and then look for fixed points?
Look for fixed points, you mean
Just when
check. You can have a symbolic executor that lets you know if it ran out of fuel. And if it ever says, I got through everything without running out, then you know it's an accurate answer. I think that's true, yeah. But, right, the number of loops might depend on the starting value of a program variable, so there won't be a concrete fuel value that gives you that outcome.
So is this already reflection, or is that what you're going to talk about?
This is like the second half of reflection, and I'll add the first half next. All right, so let's take that 3-minute break, and then I'll add the first half.
So remember I said you do need to map over the domain, so you need to know what the domain is? It's almost true.
Okay.
If you had been using those inefficient, purely functional maps, you couldn't learn what the domain is, but you could still map over it by composing functions.
Okay.
Not that you'd want to do that.
Yeah, I see.
You could.
Got it.
In practice, do you guys hit time issues more than memory issues, or?
Yes. But we do hit memory issues reasonably frequently.
Years ago in the Coq mailing list, you asked if there was anyone interested in working full-time hacking on Coq. I still have that in my draft folder of things that I might respond to you with. Did you end up hiring someone to
Yeah,
hack on Coq?
yeah, he's here.
Who is it?
It's Paul Steckler.
Ah. By the way, I know Clement. Let's see, I don't know if I remember his last name, but
That's okay.
he was an intern at Microsoft when he was there. I was working on the Daphne reference manual, and he was
Okay.
interning with Bruce Daphne.
Very cool. I should probably start again now. Okay, I think 3 minutes are up, and I'm going to get started again here. It's, where did I- So we saw this goal before in Andrew's first lecture, I think. We bring in some of the dependencies for it. It needs lists and permutations, and I'll need numbers eventually. I think you did some exercises with a permutation relation, and one example of a fact we'd like to be able to prove is that we have this list, which is the appending of two lists, one for butter, one for fly, and the catch is these aren't constant letters, they're variables standing for unknown natural numbers, and this is provably a permutation of flutter by broken into two words that are concatenated. And I have the extension to this classic grand challenge problem, butterfly 2, where of course there's a turtle that's a list of gnats, and he keeps jumping in between other words, making a nuisance of himself, but we can force him to go to the end, and we can prove that's the same. And so I'd like to have a tactic that can prove things like this. What's the fundamental reason that we can't directly use the approach that we just looked at of just running a Gaussian program to decide the answer? What's different about this one? When we were trying to figure out what are the possible outcomes of executing a program, something was different. Yeah. Yeah.
Okay. So, like in a sense, the permutation isn't like deterministic. You have to evaluate all possible permutations.
There was sort of a non-deterministic element in the last example because there were multiple different control flow paths that could have been followed, and we didn't know what they were.
Oh, right.
Yeah.
Because you know, we'll have trouble deciding equality between B and F for T and T because of the variables. And you can't tell whether they're different or not.
That's true. Once we move all those for all variables above the line, they're unknown quantities. We can't do computable comparisons on them. Yes?
Kind of going along with that, just not only is it non-deterministic, but the explosion is just so huge.
Oh, you mean if we tried to enumerate all the permutations, this might be a dumb idea.
Yes.
Yeah. I think that would be a dumb idea. Yes?
So the arguments that the functions are defined recursively on are variables in this case, and before it was a program that we knew entirely.
Yes. Maybe I'll ask for your version 2, and then we can combine these into one description.
This is quite different, actually. Though.
Okay.
The permutation was in prop world because we were trying to explain what sorting was, and normally the easy way to explain the two different things that are permutation is by just computationally sorting them, rather than by enumerating, all possible,
Right.
all possible combinations.
But we don't know the values of BUT and so on, so we can't sort by the values. We can do all sortings, and then that's just, we can compute all the ways sorting might turn out, and then that's just enumerate permutations. Yeah.
In the last example, it was already in the form of a symbolic language we could analyze.
Right. Last time, the arguments to the predicate were already in an inductive type of syntax, and that's not true here. And that's really the issue. And as I was watching Andrew give this example, I thought, hey, I should really use this in my lecture. And Wilhelm remembered he thought that before and posted some of his code for a very similar solution, which you might have seen on Slack. But don't worry, there will be no dependency on knowledge of that other approach to this. So let's define some syntax for list expressions. And I'll make this very general. It'll work for any type of data that goes inside the list. To simplify things, I'm going to require we have a default value for whatever type of data is in the list. A will turn out to be nat, and default will turn out to be 0 when we get down to these particular examples. And I'm going to define some notations when I write base var. So base vars are going to be standing for values of the type A that appear within the expression. So for instance, B, U, T, and so on are going to be base vars. And I'll also allow list variables. Those will also just be nats. And for instance, in butterfly 2, turtle is an example of a list var. Okay, and now let's define an inductive syntax for terms. What are some good constructors? We're trying to define a type of syntax that will capture everything we see here, and in those positions for the next example, and many other related ones. What are some good terms to put in here? We need to include enough syntax to let us compute what we need to compute to decide whether two terms are permutations of each other. Nil's a good one. Okay, that's a good start. Cons. What are the arguments of cons? Okay, so the A-type thing that's being cons down to the front will represent as a base var. We don't need to know anything about it to do this computation. And then we're going to have the rest of it. What type should that have? Yeah, it'll just be another term. And we'll have appending. What should these arguments be? List vars, I think I like better terms. Let's say they're general terms. But then we can put another case for list vars. And I'm going to use uppercase letters for list vars and lowercase letters for base vars. All right, so this is a pretty good description. This definitely covers the two examples I've shown and many others. I hope you can see that by thinking through the generality of this. We need to somehow connect something like this back to the original goals we were looking at. So what other functional program might I want to define now to help us make that connection? To connect syntax back to semantics, since we're going to start with semantics, we need to make that connection. Well, what might I want to write here? Yeah, let's write an interpreter. It's going to be called, I'm going to call it term D. Somehow I got used to this, putting a capital D at the end of the type name for denotation. And I'll have it take in the values of all the base variables and the values of all the list variables, like so. And also a term, and it returns a list. So then, what do we do with all these constructors? Nil. Here's a really non-plussing kind of line. We just did a little lowercase and called it a day. So we could also have cons, where I'll just look up in the list of x's values with this default in case we don't find it. So we're going to look at the xth position in this list, and if x is off the end of the list, we'll just return the default instead. It actually doesn't matter what the default value is. We'll only use this in ways where we avoid going off the end of the list. And appending two values is pretty straightforward. We're going to take the meanings of both sides and just append them together. And similar lookup process for list variables. Okay, so let's try a smaller example to see this starting to come together. Maybe I just have A and B, which are nats. And I want to show that AB is a permutation of BA. But something's not quite right here. Maybe I need to import list notations. Okay. Let's try to rewrite this goal so that it fits so that it uses the syntax type that we've introduced. I can use a tactic called change to replace a goal with another one that sort of runs to the same final value. Well, this is not a useful change, but let's make it useful. What could I write here instead of this literal list that would take advantage of the term D function that we just defined? I want some call to term D to appear here. Let's ask first, term D takes in a list of variables. These are base variables. What should the list of base variables be for this example? Yeah. I hear AB from some corner. And we don't have any list variables. Okay. And then we have to fill in a syntax tree for the corresponding to this term here. So what would that syntax tree be?
Cons 0, cons 1, nil.
Cons 0, cons 1, nil. That sounds about right. Let's check if calc likes that. This is supposed to be a list of list vars. So I need to give in a list of A's, list of A's, term. Something's not quite right here. I guess it's because I need to leave the section first, so I'm actually allowed to decide that A has a particular concrete value. Section is called lists. Let's exit lists. And now this should work better. This type list nat is supposed to be set. Well, nat and 0. The base set is nat. The default value is 0. And because this change worked, that means that calc ran the interpreter and checked that it got back where we started. So if I mess this up and put another A in here, then ooh. Why would I extended the list of variables and we didn't use one of them, but calc is smart enough to see, don't worry, this has no effect. But if I, for instance, put these in the reverse order, then not convertible. That's good. We don't want to get too much magic here. And but then the other list I wrote is the one that goes in that position, so let's put it in there. Cons 1, cons 0, cons nil, and too many parentheses or too few, or not. What's the problem this time? 1, 2, 3, 1. I still need to put the other arguments. Okay, that makes sense. Term D, nat 0, A, B, nil. All right, so now we've rewritten the goal in a form where we have syntax trees for the list expressions we'd like to analyze. What would be the next step to take? If we want this to be proved completely automatically with some library functionality we'll build. Yeah?
You can somehow show that the ASTs are permutations of each other. You get the reified values to compute over.
Okay. Right. Turning them into this form of syntax trees is a process that I would call reification. So they are reified. And you said show. Can you be a little more concrete?
Nope.
Okay. I appreciate the honesty. Yeah.
Do we need to reify the proposition itself?
I want to build a solver specific to the permutation predicate. So everything will be hard-coded.
It could just be a pair, but we probably need to get the two ASTs as arguments to one function. So not yet.
We do want them to be passed to one function. That's true. Yeah.
Make it a normal form.
All right, so now we're getting into strategies for testing equality or equivalence of two values. One is to put them in the normal forms and see if they're the same normal form. And that is what I wanted to do. That's what I worked out ahead of time in a slightly different way than Wilhelm's solution. What do we think is a good idea of normal form for this particular problem? We can sort. And we've already assigned numbers to all the variables just by forcing that we are providing a list of the variables that are going into term D. So we can just pretend each variable is the natural number that it's associated with, and we can sort. That's definitely one approach. There's another one that I decided to do, which is basically count how many times each variable appears. And that produces a data structure in a fixed order, and then you can compare those data structures for equality. And that gives you the same kind of result. So I think I'll copy in the definition and proof of this function, since it's really just yet another functional program verification exercise and fairly orthogonal to the details of this topic. So I'll pull that in here. So we stopped at this point. I'll explain a little bit of this before we proceed, and it belongs right here. So I define a type of summaries, which is a list. Each element of one of these lists is a variable and account for how many times it appears. And these are going to funny thing about this kind of approach is you don't have to worry too hard about proving completeness kind of properties of your representation. And turns out to work to do it this way. List of variable index paired with how many times that index appears. And I do it separately for both the base variables and the list variables. And here's an empty summary. Both lists are nil. And some functions do this, and it comes down to a function summarize that, given a term, produces a summary in that form. And it turns out that equality on those summaries is decidable, proved here with a Boolean operation. And then we build a Boolean equality for summaries. And then a bunch of things go into getting the final theorems. They are, here's one theorem. It's going to be one of two key correctness properties. Summarize is correct. In particular, what is it saying? If we take the summary of a particular syntactic term and then convert it back into the actual list value, that's a permutation of the original term, where we convert that back into a list value. And then via symmetry and transitivity of permutation, this will give us the overall property that we need. And there's another theorem at the end that puts those two parts together. And we also depend on the fact that the summaries eq Boolean function is correct. Whenever it says true, then the two sides are really equal. So we can put these together into a theorem I like to call it really is a permutation, where if you're trying to prove that two different term D results are permutations of each other, where they agree on the variable lists, then it suffices to run summaries eq on the summaries of the two terms and check that that's true. Notice that summaries eq, in fact, this whole first line doesn't use the variable lists at all. It really only operates on terms whose exact structure we know. So it turns out that it really is a permutation, really is a theorem, and we can put it to use down here. So I'll copy the name of it, return to our proof in progress here. What should I do now that I have it really is a permutation? Let's just apply it. And now we're reducing this to showing that the summaries of the two syntactic terms we found are comparing as equal according to this Boolean procedure. How can we prove that? Okay, let's run simple, see what happens. Simple is not quite smart enough to make this entirely trivial, but any other ideas? Yeah, so reflexivity turns out to be a pretty smart tactic. It does all sorts of things for you to figure out when things are equal, so it would work in this case. But if we wanted to see the satisfying site of true equals true, we could instead run compute, which is the big hammer tactic that does all the possible reductions, and then it gets to true equals true, and then it's more obvious why reflexivity likes this one. All right, let's see what the proof term looks like. Again, not dwelling on the details of it. I just want to point out, here it is. It's just an application of the theorem with a little eq-refl in here and copies of the syntax trees we found. Yeah? Saved me 3 characters of typing, but now your question has clawed back all the benefits. Yes?
So it seems obvious what you've done is summary converts these things into bags, multi-sites.
Yep.
And so bags are useful in a lot of contexts. So you've got a little theory, and you're basically just asking two permutations are equal if their bags are equal.
Right.
And summary is a mapping into a bag representation.
That sounds fair. Yeah. Yeah. So in one sense, the summarization operation is converting this problem into the theory of bags, where more properties that we care about are obviously decidable. And there might be other things that could benefit from going into the world of bags, and other things we could do with bags that we could sort of take the cross product and get a lot of benefits from a library.
And in particular, bags are probably a good technical word for this, but they embody associativity and commutativity. And you could start with that instead of with binary operations if you wanted addition, multiplication, and so forth and so forth.
Right, and in fact, the code Wilhelm posted, which is based on some code I wrote for a general monoid procedure, sort of goes down that road. So you can find that linked on Slack. And the earlier version of the code in CPDT, my book. So here's a question. Before we go on and make this a one-liner that doesn't force us to write abstruse syntax trees like this, here's the it really is a permutation theorem. It's a one-direction implication from summaries eq to permutation holding. Does the other direction hold also? Could I make this, could I reverse the order saying if it is a permutation, then summaries eq will definitely tell us it is? I see a no. Why not?
Because the VS might be looking differently, but they actually say no.
Right. We have not enforced lack of duplicates in VS. That's true already for lowercase vs. It's even more complicated for capital V VS, where we're sort of concerned about not just the same list appears twice, but there are duplicates of elements shared within the different lists. So it's really hard to get a so-called completeness property for this procedure. The theorem I've proved here is what I'd call a soundness property. If we didn't allow list variables, then I think we could come up with a completeness theorem given a certain assumption. What might that assumption be? Some property of the lowercase vs list that would make, let us know this is a complete procedure if capital Vs is forced to be empty. Decidable equality, that would be sort of a tool we use to prove this property. I heard someone say no dupe, which is the Coq standard library name for a list has entirely distinct elements. Given that property, then I think we could prove, though I haven't done it, that this is a complete procedure. Namely, whenever the permutation relation truly holds, then summaries eq will return true. Because we sort of have, that's somehow proving that we've retained all the important information for this problem in our syntactic encoding, which is not yet true with the baseline here. All right, so let's add the last little bit of magic to make this kind of theorem as straightforward to apply as the ones that are just using LTAC. We don't want to ask the programmer to write things like this. We want to write a tactic that does it for us. So let's start down that road. So any suggestions from the audience of how we should write some LTAC code that's going to automate the construction of essentially, let's call it 3 main steps here, or we want to abstract over this pattern, put it in one tactic, and make it happen automatically. Yeah? The question is, does LTAC support regular expressions? I'm not sure what that would mean. How would we know? Maybe this is actually more on the humorous side of the suggestion spectrum, and I should stop my infinite loop of trying to figure it out. Okay. Any other suggestions? Yeah.
Use the match in context construct with a goal to find some expressions like append and rewrite them in terms of term D.
I like the idea of matching in the goal to find things to rewrite in terms of term D. I'm not sure we need match context to do it, because we only care about the arguments to permutation. If there are other things floating around, then they won't be directly relevant to this. So basically what we need to do is write an operation called reification that turns the original goals into syntax trees. And there are a few ingredients in that. Let me write one whose purpose might not be immediately clear, but I'll demonstrate what we're going to use this to build the lists VS and VS with different capitalizations. InList is an LTAC program. It's not a Gauliga program. That's going to tell us whether X is an element of list L. And this will sort of illustrate some ways that LTAC programs are different from Gauliga programs. If the list is nil, then sorry, X wasn't in it. If we see this pattern, and now notice this X is not a pattern variable. It doesn't bind to anything that's the beginning of a list. This is enforcing a literal equality of the list head with the value X we asked about. So in this case, true. X is in the list. In fact, it's right at the front. Otherwise, now I'll use a question mark to introduce an actual pattern variable that matches anything. The list has some tail L prime, and we should just check if X is in L prime. All right, so why do we want to use this operation? I'm going to build a function called vars of that's going to compute the different values of these variable lists. So I was calling them VS and VS. Let's do that. VS, VS. And I'll look at, so the idea is I'm going to pass in a list expression, an actual semantic calc list expression, and the current values of these two lists, everything we learned so far, all the variables we found. And if we find a nil list, then there's no change to the variables list, so I'm going to return those using this syntax. You write const or colon to inject a regular Galena term back inside an LTAC program, and I'm going to return a Galena pair as the sort of the calling convention of this function. And when I have a list, and I'll accept any non-empty list with a, what I'm really matching is a cons operator, x and l prime are the arguments. Let's figure out what are the variables of the tail of the list and pass it along VS and VS. And then I'll match on that to get out the two constituents. So now VS and VS have been extended with any new variables that we find for the first time in L prime. And then let's check. Is the head of this list already in VS? What should I do if it is already in VS? Do we have, oh, return P. Yeah, we can just return the P that we already have. That is right. That sounds like a nice succinct way to do it. And what if X is not in VS? Let's add it into VS. So like this. So that's the whole case for cons. And then app is pretty similar. Let's look at the vars of first one. Match on that. It's going to be VS, VS. I'm just shadowing variable names so I don't have to keep remembering which is the current version of something. And then I can just continue to call the second process here, starting from the where we left off with the first one. And okay, now there's a catch-all case here. This is a kind of counterintuitive step. Anyone have an idea what we should do in the catch-all case? This is not a cons, not an app. Yeah.
See if the thing that we matched on is already in big P's?
Yes, the catch-all case, anything that hits this case, we're going to treat as a list variable because we don't know anything more about its structure in terms of what our permutation algorithm understands. So we're going to do the same kind of in-list thing. I'll even copy this code, make a small change to it. Let's check if L is in capital VS. If so, then good. We can return the current lists. Otherwise, let's add L to the front of the second list. So this should be good. Let me show you what this one does. So I'm going to write a tactic called permutation, takes in the default value. And for now, I'm just going to match the goal and check that we're trying to prove a permutation. Maybe I'll put intros in here for good measure. Permutation. I'm trying to look at this and this. So let's get vars of L1 starting with an empty list of nats. Notice I have to give the type of the list explicitly because LTAC is dynamically typed and it has no way to infer what type of list this is if I don't say explicitly what I meant. List of nats. Actually, I'm going to make this more general. It'll work for permutation over any type, and I'll just match out of the goal. We put an @ sign in front of the identifier to let you give polymorphic arguments explicitly and assign names to them. So capital A here is whatever type of thing we're permuting. And I'll use that to create our two initial lists. Then match that. We should get VS and VS. And then I can let P equal vars of L2. Now using these. And then let's say I'll pose P. Pose is going to make P pop up in the context so we can look at it. Oops, period. So now let's try permutation where 0 is the default. There it is. This procedure found out that the list of base variables is AB and the list of list variables is empty. Any questions about that procedure? Whose code I will partly scroll back on screen. Here's a fun part. Any questions about this step of the process? We're almost done. Yeah?
The mitigation, why you need
Which line?
So when you up const column, yes, and capital yes. So when we add things to the list.
You mean this line right here? Or, okay.
So what is const doing?
It's kind of confusing because we're reasoning about lists that have a cons operator, but we're also using lists for bookkeeping in our procedure for reasoning about lists. This is building a list of all the variables as distinct from the lists we're trying to permute. I don't know if that helps.
Okay, I think I know what you mean. In the current context where we're matching, we're writing alt-text code. But so whenever we do a match, what it expects in the match result is a tag. But what we want is to give a term in Galena. So we use the const to provide a Galena term instead of using tag.
Does that answer your question?
A little bit, but maybe I have to read a little bit more about what they use.
Okay. Yeah.
Can you say again why we need the catch-all part there? I didn't get that.
The catch-all, this is a turtle trap. It's going to catch this turtle here. It's any expression that is not built from the other things. All right, so we're almost done here. We have these lists, and now I just need to implement finally, the translation into syntax trees from regular calc terms, and I'll call this reify term takes in, or use different names for those, takes in those lists we just computed, and they won't actually change throughout our recursion here. And what we do is we check if we see a nil, turn it into a nil. If we see a cons, well, now I'm going to need another operation that looks up what position of a list a value appears in. So what numeric position of XS does X appear in? Well, if it's at the front, then it's in position 0. Otherwise, what we should do is get the position in the tail of the list and then add 1 to it. All right, so we have this thing here. Let's get the position of E in V's, and let's recursively translate the tail, and then just put them together, cons XE prime. And then very similar thing happens for append. And what it is let E1 equal reify term VS E1, E2 equals this, and put those into an app. The catch-all case is going to be for list variables. And let's just look up the current term in the list of list variables. And then this is a var x. I meant that. Okay. So this is good. What did I do down here? I think I started writing something relevant to this. Let's move this later so I can use some of the new goodies we came up with. We have that way to reify a term. So we computed the variables. That's good. And let's match these variables and get the two lists. And now we decided L1 and L2 are the two list expressions. So let's get L1 is the result of reify term VS L1. L2 is reify term for L2. And now we can change to permutation term D VS L1 term D VS L2. Let's try that after I put enough n's in it. Change and something else. Last term evaluation failed. That's interesting. Let me try another debugging trick. I'm going to pose L1 and pose L2 so those pop into the context and we can see what happened. Found cons 0, 1, nil, cons 1, 0, nil. That looks okay. What's wrong here? I'll just doing the equivalent of printf debugging here and printing some bits of information I'm curious about. These should be the terms that we tried to change things into. So why didn't it work? Now it doesn't even like the type checking of those or something. Term AB. Oh, I forgot to give the other arguments, which are A and the default, because the whole thing is parameterized by the carrier set. This should work better. Okay, so that type checked. I can go back to this now. All right, so now we've replicated these first two lines from before. You can see this is exactly the same goal as we manually typed in. And it's in this nice syntactic form, where all we need to do is apply it really as a permutation and then use reflexivity. So let's add that to the tactic. And ta-da, permutation. And you know what? It does this one. That's the same one. It does this one too. With a nice short proof term that just restates the goal with syntax trees. Questions? Yeah.
This is maybe too low level to be interesting, but the awesome thing, we didn't need to use conster when during the zero case. Was Apex smart enough to figure out this has to be a Galena term?
There's something special about identifiers where you don't need to say whether it's a tactic or a Galena term. The parsing rules are the same. They're the same identifier conventions in both sublanguages, so maybe that's why. Yeah?
So we've been using the same variable sets that have been collected for both terms that are constructed.
Which is important.
Okay, that's what I wanted to ask, because could it be that it breaks now if we have something which actually is not a permutation?
Interesting question. It's always good to ask what happens when the procedure is not expected to succeed. I'll copy this and we'll try that out. It definitely should not prove a false theorem. Can we prove conservation of turtles? Let's see. Reflexivity failed. Unable to unify true with the result of our big procedure that tests if things are permutations. So recall, really, this, when we apply this theorem, we get this hypothesis that the summaries eq procedure returns true. When we have a false goal, then summaries eq will return false, and reflexivity will no longer establish false equals true. Yeah?
In the permutation tactic, you collect one set of variables from both sides of the permutation, or do you collect
One set for both sides. Yeah, that's important. Yeah, right. So we have LTAC permutation. So we get the vars of for L1, and then we take those, the outputs of that, and make them the inputs for vars of L2. Yep. All right. Proof by reflection is identifying a class of goals, defining a type of syntax trees for those goals, defining a Galena procedure that computes on syntax trees, proving it sound, doing reification, and plugging it together in this way. Yeah?
Is that the kind of thing SS Reflect does?
So the SS is for small scale, and most of what they do doesn't look like this exactly. They try to do a lot of computable Boolean numeric things, but I don't think they have much conversion of terms from some baseline semantic things into syntactic trees, as far as I know. Yeah?
Can you reify more of Galena, like functions, or?
Sure. It's more. Can you reify everything? Yes, but proving various meta theorems about the language inside itself is known to be impossible by Gödel theorems.
Do you, for example, count something in your, like if you had these data structure things and you had these functions, and if you wanted to count reductions or something?
Count reductions. Well, counting reductions is not well defined in Galena. You want to count how many.
So I want to reify the Galena function into a form that allows me to write in my own interpreter that counts reductions.
Sure,
And
you can do that.
something about how many steps they take or something.
That is definitely in scope. Again, you won't be able to prove its sound for the full Galena language because that's a very deep meta theorem, and we know it's impossible to prove languages sound inside themselves if they're expressive enough, but you can get pretty far. Definitely run out of time. I'll take a few more questions, though. Yeah.
Could you clarify what is the advantage of this approach and when it doesn't work so well?
One advantage, you can define a procedure and prove it always works correctly. With LTAC, you might find dynamic type errors popping up when you apply it to a new goal. Also, you get this property that I showed at the bottom here, where this proof term is quite small. It really just restates the goal. It doesn't grow with the complexity of the goal. That can make a big difference for performance. But as someone pointed out in an earlier comment, with the LTAC everywhere approach, it's easier to get certain kinds of flexibility and extensibility. So reflective procedures tend to be relatively rigid compared to LTAC scripts of the other kind. That's what I think of off the top of my head. Any more questions? Yeah.
So you mentioned briefly that you can get that sort of extensibility that you would have got from LTAC scripts. Can you just give like a high-level description of like the general approach to this?
I'll be demonstrating it in my next lecture.
Okay.
Not explaining it too much, but you'll see the payoff. All right. Thank you.